Hi everyone, in this video we will be discussing probably the most important theorem of probability theory, and that theorem is Bayes' theorem, or it is also called Bayes' law. This theorem provides a very fundamental technique to compute the probabilities in very practical scenarios. Before going into the proper formulation and definition of Bayes' theorem, it is necessary to understand theorem on total probability. What is theorem on total probability? To understand this, let us consider this Venn diagram which is showing you a sample space, and let us assume that there are three events B1, B2 and B3 with two conditions. Condition number 1 is that these three events constitute the complete sample space as shown in this Venn diagram, and condition number 2 is that all of these three events are mutually exclusive, means their intersection with each other is equal to 0. So if these two conditions are satisfied, it means theorem on total probability can be applied. Now assume another event occurs, and that event is, let's say, A, such that this event A has some intersection with one or more of these three events. In this particular case, as I have drawn the event A, it has some non-zero intersection with all the three events B1, B2 and B3. Now if I am interested in computing the probability of this event A, how can it be found? From Venn diagram, it can be easily seen that this probability of A will be equal to this shaded region, this one and this one. Now you see, the first shaded region is what? It is basically A intersection B1. What is this one? This is A intersection B2. And what is this one? It is A intersection B3. So I can write here that probability of A is equal to probability of A intersection B1 plus probability of A intersection B2 plus probability of A intersection B3. And now, by using the definition of conditional probability, as conditional probability is defined as probability of A given B equals probability of A intersection B divided by probability of B. So from here, I can write probability of A intersection B equals probability of A given B multiplied by probability of B. So with this definition of intersection, I can rewrite this probability of A as probability of A equals probability of A given B1 into probability of B1 plus probability of A given B2 into probability of B2 plus probability of A given B3 into probability of B3. Now if I generalize this statement by writing a summation starting from I is equal to 1 to n, and assuming that there are now n such events B1, B2 up to Bn, and all of those events are mutually exclusive and they constitute the complete sample space. With these two conditions, I can write here that probability of A given Bi into probability of Bi. So you see, by using this formulation, I can find the probability of event A, and this statement is called theorem on total probability. Now with this definition of theorem on total probability, we move towards the formulation of Bayes' theorem. So from this Venn diagram, it can be seen that these events B1, B2 up to Bn, they are called a priori events. Why these events are called a priori? Because they occur before the occurrence of A. Now after the occurrence of A, if we are interested in computing the probabilities of these events after the occurrence of A, means what? Probability of B1 given A or probability of B2 given A, and so on. If we are interested in computing these probabilities are called a posteriori probabilities. Now, how to compute these a posteriori probabilities? This is a major problem, because if we write this thing in the form of conditional probability, what it comes out to be? Probability of bi given a. By using conditional probability theorem, I can write it as probability of bi intersection a divided by probability of a. Right? Now, in the numerator, because it is intersection, and intersection is always commutative, so I can rewrite the numerator as probability of a intersection bi divided by probability of a. Now again, by using the theorem on conditional probability, I can write the numerator as probability of a given bi into probability of bi divided by probability of a. Now you see, we have transformed the unknown probability into some quantities which are already known and can be computed easily. How? If you see, this probability of bi is already known. Why? Because this is a priori probability. And this probability of a, how can we compute this probability of a? You see, this can be computed by using theorem on total probability. So it is basically total probability. And what about this probability of a given bi? This probability can also be computed easily because the condition is applied on the a priori events, right? So it can be computed. So the unknown probability can be transformed in this way, and this particular equation is referred to as Bayes' law. So now, what is the significance of this Bayes' law? As you must be very clear with this discussion that whenever we have certain number of events greater than or equal to 2, such that all of those events are constituting the complete sample space and all of those events are mutually exclusive, and if another event occurs which shows some intersection with one or more of those a priori events, and if we are interested in computing the probabilities of those a priori events after the occurrence of a, then we need to use Bayes' theorem, right? This is a very significant implication of Bayes' theorem. So what are the conditions? Conditions are: number 1, that the events b1 up to bn, they are mutually exclusive, means their intersection is equal to 0 with each other. And condition number 2 is the same events constitute complete sample space. Now I will show you this significance and this implication with the help of an example, and it will be a very practical example. From that example, you will completely understand how to apply Bayes' theorem in such scenarios. Now this is the example that we are going to solve by using Bayes' law. And this problem states that a diagnostic test has a probability 0.95 of giving us positive result when applied to a person suffering from a certain disease, and a probability of 0.1 of giving a false positive when applied to a non-sufferer. It is estimated that 0.5% of the population are sufferers. Suppose that the test is now administered to a person about whom we have no relevant information relating to the disease, apart from the fact that he or she comes from this population. Calculate the following probability that given a positive result, the person is a sufferer. Now, first of all, we need to identify that whether this problem can be solved with Bayes' law or not. What kind of information is given to us? So, first of all, we need to extract the information. And the first information that is given to us is that a test has a probability 0.95 of giving a positive result when applied to a person suffering from a disease. So, it means we need to define some events. And let's say the first event is S, and that event is that the person is sufferer. Similarly, we can define another event NS and say that this event is that person not sufferer. And now we define another event P, and that event is that the test is positive, and we define another event which is N, that the test is negative. So now from the information we can see that this thing, it is estimated that 0.5% of the population are sufferers. It means that probability of S, it will be equal to 0.005, and because all of the population, there are two possibilities only. Either they are sufferers or they are non-sufferers. It means if we draw a Venn diagram and say that this is S and this is NS, means either they are sufferers or they are non-sufferers. There is no third possibility. It means these two events are mutually exclusive. If a person is sufferer, it is not possible that he or she is non-sufferer at the same time. It means both of these events are mutually exclusive, number one. And number two, both of these events are constituting the complete sample space. It means those two conditions are satisfied. But here, probability of person not sufferer is not given, but since both of these events, they are constituting the sample space, it means probability of NS will be straight away equal to 1 minus probability of S, and that is 0.995, right? Now these two quantities we have already calculated. Now the next thing is probability that the test is positive given the person is sufferer. Now we have to find where this information is given. So we can see that a test has a probability 0.95 of giving a positive result when applied to a person suffering from a certain disease. It means this is the probability and it is given to be 0.95. Similarly, in the next statement it is written that a probability of 0.1 of giving a false positive when applied to a non-sufferer. It means that probability that the test is positive but it is false positive when applied to non-sufferer is 0.1. So these two probabilities are already given to us. Now what probability we need to compute? This is the most important thing. Calculate the following probability that given a test positive result, the person is a sufferer. So given positive result means we have to compute given positive and the person is sufferer. It means we have to compute this probability. Probability that the person is sufferer given the result is positive. Now we can see that we are going to compute the probability of a priori event after the occurrence of another event, and that event is that the result is positive. It means I can draw here another event and name it as P. So the test is positive. Now you see, this is another event which is occurred after the occurrence of a priori events, and since if the test is positive, it can happen that the person is sufferer, which is shown by this area, and it can also happen that if the test is positive and the person is not sufferer. So it can have intersection with both, right? Now after the test is conducted, if we are interested in finding out the probability that the person is sufferer given the test result is positive, it means we are going to compute posteriori probability. So this particular probability is posteriori probability because it is being computed after the occurrence of another event A. You can directly map this Venn diagram and this Venn diagram, and you can directly compare. So instead of B1, B2 and B3, in that problem we have S and NS, and instead of this event A, in place of this event A, we have got the event P, that the test result is positive. So instead of computing this probability, there we are going to compute probability of S given P. Now you can directly apply the Bayes law and write this probability of S given P as probability of P given S multiplied by probability of S and divided by probability of P, right? Probability of P. So this denominator will be obtained by theorem on total probability. So we can also write it as probability of P given S into probability of S divided by, in the denominator we will use theorem on total probability, probability of P given S into probability of S plus probability of P given NS into probability of NS. So because we have two mutually exclusive events, therefore in the denominator we have got two terms. Now you can simply substitute the values. Probability of P given S is equal to 0.95 multiplied by probability of S was 0.005 divided by the same thing here, 0.95 multiplied by 0.005 plus 0.1 multiplied by 0.995. So if you solve this fraction, it can be shown that the result of this fraction is 0.0456. So this is the probability that the person is sufferer given the result is positive, which is very low. It shows that the test result is not very trustworthy, right? So this is how you can apply Bayes' law in practical problems while computing the probabilities of posterior events. So that's all for this video. Thank you for watching. Stay tuned to our channel.